So, welcome student to the next class of Introduction to Nonlinear Optics and its application. So, in the previous class we studied that how one can generate second harmonic in the crystal like KDB crystal. So, one important thing there we find is that the launching angle of K. So, K is in such a direction that it matches the phase matching is there, but also we need to find out a suitable azimuthal angle. So, this suitable azimuthal angle eventually increase the D values, and that is why instead of writing D we find D effective, and also we find out that these D values in a D matrix there are several D values are there, but finally when second harmonics are generated only one or two D values are there which are basically responsible for that. So, not all D value are used, only one or two D values may be used to generate the second harmonic. So, in the previous case we find that for generating second harmonic the orientation of K is important, and also the direction of Pz is important. So, Pz is in z direction, but that will not going to give the desired second harmonic, because our condition is two ordinary wave will generate extraordinary wave. So, z direction was not the direction of extraordinary wave. So, we need to divide this component in such a way, the Pz component in such a way, one direction of the Pz component can generate the extraordinary wave which is at 2 omega frequency, then only we can generate the second harmonic properly. So, we will extend this concept. So, let us see what we have in today's lecture. So, today we will going to learn the second harmonic, but not in KDB crystal, in a different crystal. It is called the lithium niobate crystal. So, this crystal has different properties, different D matrix. So, obviously, the condition of phase matching will going to change, and also the launching angle and other issues will be there. So, how do we take care of that issues? So, we will going to discuss in this particular lecture. Okay, so go back to our slides. So, this is the D matrix structure of lithium niobate. So, we can see that only 3 distinct elements are there in the D matrix. So, in previous lecture, from the previous lecture we already find that this D matrix is start with 27 independent components, and then by applying the symmetry it can reduces to 10 components, and then further if I introduce some symmetry like Kellman symmetry, or using this Neumann principle where we can put some kind of operation over this D matrix, and as a result we will find that few of the D matrix components are 0 and there are few non-zero elements, and these non-zero elements are important. Here we find there are few D matrix, few elements of the D matrix, 3 elements are there, 3 different elements are there, but most importantly these elements we should look D33. This is the element which has the maximum value. So, this is really, so what is the value of D33? So, D33 is of the order of 30 picometer per volt, which is really a large value compared to the other values. This is almost 10 times bigger than the D22 and more than 10 times rather, and 1.5 times or so bigger than D31. So, obviously, these two things 5 times bigger than this rather. So, these two if I compare these components, we can find that D33 really having a large amount of D values. So, we know that the efficiency is directly proportional to these D components or these D values which are involved in the second harmonics. So, from the beginning our aim should be how to make our system so that D33 should involve in generating second harmonic. So, that is our aim, that how that second harmonic will be involving through D33, that we need to think of. Well, also one thing I should mention here, that this particular structure in non-critical phase matching system, the k vector is almost in the direction of x vector. Why I am writing or showing this figure is important, because for lithium niobate system the refractive index is temperature dependent. So, ordinary and extraordinary refractive index is depending on temperature. So, by varying temperature there is a possibility that we can make the condition, we can really make the condition NO of omega is equal to NE of 2 omega, but not any theta involvement. So, that means this angle should be pi by 2, and that one can achieve in lithium niobate system. Okay, so, let us see what we have in the next slide. So, in the next slide basically we plot the refractive index for this lithium niobate structure, and this refractive index plot suggests that at particular wavelength, say if I look very carefully, here we have some wavelength say around 1.2 or something, and here we have, this is the value of n lambda. So, this is n of omega, which or m, let me write once again. So, this say n of lambda equal to say around 1.2, and if I go back here in this point, so this value is the same value of whatever the value we have here. This is n, this is ordinary. So, I should write O. So, this is n E, because this is over extraordinary line, n of E of lambda equal to say around 0.6, which is half of that. So, that means if I write in terms of frequency, n O at omega is equal to n E at 2 omega, which is a condition that one can achieve when the phase matching is critical in nature. That means k vector is moving along x direction, where these 2 points are coinciding. So, these 2 points are coinciding. So, there is no theta dependency here. So, that is the direction where we should launch our light. So, if I do that, then this non-critical phase match has some facilities. Since it is a non-critical, k vector and s vector both will follow the same. So, s vector is also going to the same direction. So, these are additional advantages that we have. So, if we have this kind of phase matching issues, then we need to find out few other things. So, here we, whatever we have discussed, it is written in a compact form, in a note form. So, what we have, let me read once again, that D33 has a maximum value. So, our M should be D effective proportional to D33. As I mentioned that the second harmonic should be in such a way that it should be proportional to D33. Now, O wave always perpendicular to the optic axis and the propagation direction vector k, that you should always know that whenever we calculate the second harmonic, and if it is OO plus E system, then we should be careful that the fundamental wave should be ordinary wave, and the generated wave, that is 2 omega wave, the generated wave which is having the frequency 2 omega should be extraordinary. So, that thing we should remember, and we should do these things very carefully, that how these waves are generated. For lithium niobate crystal, NO is greater than NE, as I mentioned, and it is a negative kind of crystal, and since it is a negative kind of crystal, the phase matching condition that one should have is OO plus OO tends to E system. So, this is a scheme through which the second harmonic should generate. And as I mentioned, for lithium niobate crystal, by adjusting the temperature, there is a possibility that we can have NO omega and N2 omega, that we have already shown, and that means my phase matching angle is around pi by 2. That means k is making pi by 2, or k is perpendicular to the optic axis, and that is the direction along which we have phase matching. So, next we will try to understand the second harmonic generation in two different cases, like we have done for KDP crystal. Here the two different cases are, in first case the electric field is now z direction. If the electric field along z direction, it is perpendicular to the k, because k is along x direction. So, this is one possibility, because k has to be in x direction, the phase matching is in this direction only. So, electric field that we can launch, this is a trivial case that I launch in z direction. Now, if the electric field is launched along z direction, so readily you can understand that this fundamental electric field is not a ordinary wave, this is an extraordinary wave. But anyway, if this is the case, let me figure out what should be the value of Px, Py, Pz. But from the beginning we know that this wave is extraordinary wave, but still we need to figure out what is going on here to understand the system. So, Ex is 0, Ey is 0 and Ez is 1. This is our field the field components, x, y, z components of the electric field. Now, if electric field components are this and D matrix, which is already given on the previous slide. So, Px, Py, Pz for second harmonic we can write this in the matrix form, and if I write this in the matrix form, only the y component will going to survive, all the other component will be vanished, because Ex and Ez are there, sorry, only z component will be survive, the other two will going to vanish. Now, here unlike the KDP crystal, we can see there are many non-zero D elements are there. In that case only 3 terms were there which was non-zero, most of the cases the 0 coefficients were there. So, that is why most of the terms was 0, but here there is a possibility that we have some kind of non-zero term, and indeed we find that Px is equal to 0, Py is equal to 0 and Pz that is generating which is not 0 and also proportional to D33. That was our initial aim, that my polarization at second harmonic or polarization at 2 omega should be involved with D33 coefficient. So, D33 coefficient should be involved in generating the second harmonic, and here that is the case. So, that means my polarization would generate a second harmonic along this direction, propagation will generate a second harmonic along this direction, because Pz is along this direction. So, it will going to generate a 2 omega along this direction. Now, the important question that we have already mentioned before starting this discussion, that what is the what kind of wave E2 omega is. E2 omega is perpendicular to k and it is along the z direction, it is along the z direction. If it is perpendicular to the k and if it is along z direction, so z and k are in same plane. So, what should be the direction of ordinary wave? Ordinary wave is along y direction, that we first need to figure out. This is the direction of ordinary wave. Ordinary wave is along y direction, that is for sure. If ordinary wave is along y direction, k is along z direction, what should be the direction of extraordinary wave? We know that extraordinary wave is perpendicular to ordinary wave and k, that is the rule. So, in this particular case extraordinary wave will be along the z direction. So, that means E2 omega which is along z direction, which is our second harmonic field that is generated by Pz2 omega, the z component of the polarization, is eventually an extraordinary wave. So, I should put a E here. Now, we can easily find that the fundamental wave which is generating is extraordinary and the second harmonic that is generating is also an extraordinary wave. If two waves are extraordinary, the phase matching condition. So, we will never going to have two extraordinary wave to merge an extraordinary wave. This is a frequency omega, this is a frequency omega, this is a frequency of 2 omega. Then my phase matching condition would be n of extraordinary of omega will be n of extraordinary of 2 omega, which never possible. So, that means the phase matching angle we make in this way, but there is a possibility that I can generate E along z direction, I can launch E along z direction. Also P z is not equal to 0, that means P z is still generating. P z is generating means it will going to generate a second harmonic wave along z direction. So, second harmonic wave can also generate along z direction, there is a possibility, but that will going to contradict the fact that my phase matching things where E n of E omega should be equal to n of E 2 omega, which basically not possible. So, even though all the terms are non-zero, we will not going to find any kind of second harmonic. So, that is a very important example, even though it looks quite trivial from the beginning, but we should understand the fact that if the term is non-zero, that does not mean every time it will going to generate second harmonic. So, there are a few conditions that should follow, and this condition when followed strictly, then only the second harmonic generation is possible under this birefringence phase matching. So, that means second harmonic generation is a very critical phenomena, and you have to be very careful in generating the waves and second harmonics, and you should know the physics behind that, and every time you should keep that in mind. So, in the note we mentioned that the polarization component P z will generate a electromagnetic wave having the frequency component 2 omega with polarization along y direction along optic axis. That means the generated wave is actually an extraordinary wave, as we mentioned. The generated 2 omega wave and the fundamental wave omega wave both are extraordinary, and that is the reason why the phase matching should not be. So, there should be a 2 omega here, it is again a typing mistake. So, n of omega will be never equal to n of 2 omega. So, that means this orientation of E is not a valid orientation. So, we need to do something new. So, now what we were doing, that we are launching the electric field making an angle phi with the z axis. So, previously E was in z direction, now E is in arbitrary direction with an angle psi. The figure is shown here. E is k is along this direction, this is the direction along which the phase matching is there, but the orientation of E basically is important. Even though the phase matching is there, P z is not equal to 0, still we find that there is no electric second harmonic generation. So, here we need to find out what is going on in terms of this E. So, E is launched with an angle psi. So, that means we can figure out what are the components. So, first thing we need to find out what are the components. So, E x should be 0, because E is eventually in y z field y z plane. E y is the component along y direction. So, it should be E 1 sin phi sin psi, and z is E 1 cos psi. Now, you need to be careful enough to write this component in terms of ordinary and extraordinary, because along y direction we mention it should be a ordinary wave. So, I write this E 1 sin phi is a component that is generating ordinary wave, and the other component which is along z direction should be the extraordinary wave. That issue we have already deal with in the we have already discussed in our previous slides, that if the electric field along z direction, the electric field is an extraordinary wave. So, here that is the z component is the extraordinary wave. So, once we have the E x, E y, E z, the next thing is to find out my polarization. Now, you can see that there are many non-zero terms sitting here. So, E x was 0, E y was not 0. So, I put this, E z was not 0, 2 of E x E y, 2 of E y E z is not 0, but other 2 terms is 0, because both the cases it is involved with E x term. So, now if I calculate term by term, so P x turns out to be 0, there is no P x. P y, there is a combination of term. If I calculate P y, how to calculate? This multiplied by this 0, d 2 2, this is non-zero, this is this 0 multiplied by this is 0, d 3 1 multiplied by this is again non-zero. So, this term and this term, 2 terms are there, and also we find out what is my P z. P z is 3 1 1 and another is d 3 3 E 1 cos cot theta. So, there are many terms are there, are many terms that is in this matrix. So, as a result we have different term in P x, P y and P z. So, P z is containing 2 terms, P y is containing 2 terms and P x is containing no terms. So, it is 0. So, now you should be careful enough to find out that what is the combination. So, in both the cases if I find it is E 1 square sin square theta. So, that means E 1 sin theta. Okay, here is a notational problem actually. Here I write it psi. So, it has to be psi, but I have written is theta. So, let us consider this angle is theta. So, this angle should be theta, this angle should be theta. So, if I consider this thing here, that sin square theta E sin E 1 sin square E 1 square sin square theta is basically the components of ordinary wave. So, 2 ordinary waves are merging to generate the polarization along y direction. Also here we have E 1 square sin theta cos theta. So, that means here we eventually have one ordinary component of field, one extraordinary component of field. So, ordinary plus extraordinary component can generate polarization along y direction, and in P z also 2 ordinary waves are generating, and as a result I am getting some kind of wave, some kind of P z. Here also in the similar way 2 extraordinary waves are combined to generate the P z term. So, here one by one if I consider, so you can understand that these 2 ordinary. So, what should be the electric field associated with P y? P y will going to generate an electric field of 2 omega along this direction. This is electric field along 2 omega and the direction is y. So, that means this has to be an ordinary wave. So, 2 ordinary wave will going to generate something ordinary, which is again violating the phase matching. So, this term, the contribution of this term will not be there. But here we have a situation where one ordinary and one extraordinary wave can generate an ordinary wave of 2 omega. This is omega of ordinary wave, this is omega of ordinary wave, it will going to generate a ordinary wave of 2 omega. This is a type 2 kind of phase matching. So, type 2 kind of phase matching is here. What about P z? 2 ordinary wave, P z will generate an electric field along this direction. This is the direction of extraordinary wave which is generating 2 omega. So, once we have electric field 2 omega along z direction, that means this contribution will going to generate an electric field which is extraordinary in nature. So, what should be the scheme here? The scheme is ordinary plus ordinary which is generating extraordinary. So, this is the frequency component omega, this is the frequency component omega, this is the frequency component 2 omega. So, this is also valid. So, this term is also valid. What about the last term? Last term again 2 extraordinary wave will going to generate P z, P z will going to generate an extraordinary wave. So, extraordinary 2 wave will leads to one extraordinary wave of 2 omega. So, omega it will going to generate 2 of omega. So, again it is violating. So, this is 2 of omega, again this is violating because the condition is not valid. So, once we know these components carefully, then we can readily find out that what is going on. So, now as I mentioned, this term, this shaded term is a type 2 kind of phase matching, where P y leads to generation of second harmonic along y direction, we call it E 2 y. So, which is a ordinary wave, and E 2 omega is generated with the combination of one ordinary wave of frequency omega, that is the first term here, and another combination of 2 omega, which is the second term here. So, first term was E 1, first term was, again this notation was, it should be either it should be theta or it should be psi. So, there is a notational mismatch, but anyway. So, this angle is theta, if this angle is theta. So, E 1 cos theta is along z direction. So, this is an extraordinary component, and E 1 of sin theta is ordinary wave because it is along y direction. So, both the cases it is the omega component. So, these two combination, basically one ordinary and one extraordinary wave generate this term, and this term basically gives us a type 2 kind of phase matching. Well, we are almost in the end of this class. So, type 2 phase matching, if I look carefully what is going on. So, in this picture, so in type 2 kind of phase matching, the wave vector k omega of ordinary wave, the wave vector k omega of extraordinary wave, they will going to merge and generate k omega of an ordinary wave. That is one combination, but you should remember that another combination is still possible. So, we have already learned that. So, there are two possibilities, ordinary wave plus extraordinary wave can lead to an ordinary wave, or ordinary wave extraordinary wave can lead to one extraordinary wave. Both the cases the phase matching can be possible, and this kind of phase matching is called type 2 kind of phase matching, which we just learned in the example that in the second harmonic generation one part of type 2 phase matching can be possible, and the refractive index, in terms of refractive index we have the relation between the refractive index like this is a phase matching condition in terms of refractive index. If we plot the vector diagram, you can see that one ordinary, one extraordinary wave, they can merge to generate one ordinary wave. And in the figure also we can see that if I launch an electric field in this direction, when it pass through the system, if it generate the electric field which is ordinary in nature, then it will vibrate along this direction. So, we will start from this electric field, launch electric field, but the second harmonic field will change its polarization state, and ordinary wave that will vibrate in y direction, it will be in y direction. So, this will be a schematic figure to show how the second harmonic will be generating in lithium niobate crystal, where type 1 and type 2 phase matchings are there together. So, with this note, let me conclude here. So, we have learned a very important in the last two classes we have learned very important problems. One is second harmonic generation in KDB crystal, and in second harmonic generation in lithium niobate crystal. And in lithium niobate crystal we find the orientation of the K is fixed, but if I change the orientation of E, then there is a possibility to generate type 2 kind of phase matching. So, with this note, let me conclude here. So, see you in the next class, and thank you for your attention.